The proper operation of a compressor system depends on instrumentation and control devices. For example, these devices allow the compressor to be started or stopped. They provide information about the compressor's operating conditions. They maintain the values of process variables, such as the compressor's discharge pressure. They keep the compressor operation stable. They prevent overload of the compressor's driver. And they can shut down the compressor if unsafe conditions occur. Many compressors are started and stopped from a control panel. This control panel also has controls to regulate the speed of the compressor, and indicators that provide information about the compressor's operating conditions. This one displays lube oil pressure. The control panel also contains alarms that let personnel know when abnormal and potentially damaging conditions exist. For instance, this alarm is for high gas temperature. Compressor instrumentation and control devices also maintain the gas discharge pressure. For example, this simplified illustration shows an axial compressor with one type of control system that maintains a constant discharge pressure. The main components of this control system are a pressure controller and inlet guide vanes. The arrows indicate the flow path of the gas through the compressor. The pressure controller has a pressure sensor that senses the pressure of the gas in the compressor's discharge. If the discharge pressure deviates from its desired value or set point, the controller sends a signal that opens or closes the inlet guide vanes. As long as gas flow through a compressor matches the demand for gas, the discharge pressure also remains constant. When the demand for gas increases, discharge pressure begins to drop. The pressure controller responds to the change in pressure by opening the inlet guide vanes, which allows more gas to enter the compressor. When more gas enters the compressor, more gas can be compressed. As more gas is compressed, the discharge pressure increases until it returns to its desired value. On the other hand, if the demand for gas decreases, discharge pressure increases. The pressure controller responds to the increase in pressure by closing the inlet guide vanes. As a result, the flow of gas into the compressor is reduced. Less gas is compressed, and the discharge pressure returns to the desired value. So, by adjusting the flow of gas into the compressor, the control system maintains the discharge pressure of the compressor at the desired value. For a given discharge pressure, a compressor has a certain minimum flow rate. Below this flow rate, the compressor becomes unstable. A decrease in flow below the minimum flow rate can cause a series of momentary reversals of flow through the compressor. This situation is called surge or surging. The symptoms of surging are unmistakable. Surging results in violent fluctuations in discharge pressure. And when an electric motor is used as a driver, surging can cause extreme variations in motor current. Other symptoms include low system gas flow, excessive vibration, and a muffled banging sound inside the compressor. If surging is not corrected, it can cause serious damage to the compressor. To prevent surging, the flow rate of gas through the compressor must be kept above the minimum stable flow rate, or surge point as it's commonly called. One method that is used to maintain this flow rate when the demand is low is to recirculate a portion of the compressor's discharge back through the compressor. This simplified illustration represents an axial compressor with a common type of surge control system. The control system consists of a flow sensor in the compressor's discharge piping, a flow controller, and a recirculation valve that's located in a section of piping between the suction piping and the discharge piping. When low demand causes the gas flow rate to approach the surge point, the flow sensor sends a signal to the flow controller. The controller then opens the recirculation valve and routes a portion of the discharge gas flow back into the suction piping. When a portion of the discharge gas flow is routed back into the suction piping, the gas flow through the compressor increases and it stays above the surge point. When demand increases, gas flow through the compressor also increases. when the gas flow is high enough to prevent surge, the flow controller closes the recirculation valve. The gas flow from the compressor is then directed only through the discharge pipe. In this topic, we looked at the functions of instrumentation and control devices commonly used with centrifugal and axial compressors. We also saw how surge control can be achieved. Most centrifugal and axial compressors operate at very high speeds, usually several thousand revolutions per minute. So they must be started up and operated properly, or they can be severely damaged. A compressor startup consists of a series of steps. These include preparing the compressor for startup, warming up the compressor, and starting the gas flow to the compressor. The warm-up is continued as the compressor is brought up to operating speed. In our example, the compressor is used to compress a gas that is supplied from storage tanks. Many compressor startups are performed by more than one operator, so good communications are essential. Before the compressor can be started, operators must verify that the compressor's gas supply is available and that the controls are set in the proper positions. Another important part of preparing a compressor for startup is performing what's called a valve lineup. Performing a valve lineup means making sure that all of the valves associated with the compressor and its auxiliaries are in the proper positions. For example, this operator is opening the oil supply valves in a compressor lubrication system. These valves must be open to supply lubricating oil to the compressor. Once the operator is sure that all of the valves are properly set, he starts the compressor auxiliaries and makes sure that they're operating properly. For example, this lube oil pump has a steam-powered driver. It's started by opening the valve that supplies steam to the driver. Then, to make sure that the pump is working correctly, the operator checks the lube oil supply to the compressor. One way to do this is to make sure that the oil is at the proper pressure. In addition to starting and checking the auxiliaries, the operator also checks the compressor to make sure it's ready to be started. He checks the equipment for abnormal conditions, such as loose or missing parts. This compressor is driven by a steam turbine. The compressor handles a flammable gas, so it must be purged with steam or an inert gas such as nitrogen. The operator does this by opening a manual purge valve. Purging removes air from the compressor and reduces the risk of an explosion or a fire. Once the compressor has been purged, it is started and allowed to warm up. The steam turbine is started at a low speed to allow the compressor to warm up. The steam turbine is started by opening the steam supply valve. As the compressor is warming up, it's important to make sure that the proper flow of cooling water is maintained to the lube oil cooler. The compressor could be damaged if the lube oil temperature is allowed to get too high. The internal parts of the compressor and its driver must warm up gradually to prevent stress and potential damage. For this reason, it's important to keep a close watch on compressors while they're warming up. Once a compressor and its driver have run for a while at a low speed, the compressor can be brought up to operating speed. This involves increasing the speed of the compressor at a certain rate, which is called a ramp rate. The compressor and the driver will continue to warm up as speed is increased. Increasing the speed according to the ramp rate ensures that the compressor's parts warm up evenly. As a general rule, it's important not to exceed the ramp rate while a compressor is being brought up to speed. However, in many centrifugal and axial compressors, certain rotational speeds, called critical speeds, cause severe vibration. This vibration is caused by the physical characteristics of the compressor's rotating parts. The vibration can be severe enough to seriously damage a compressor. Critical speeds are often identified in a compressor's operating procedures, and they occur when the compressor is at less than full operating speed. When a critical speed is reached, the ramp rate is usually increased to pass through the critical speed as quickly as possible. This action limits the time the compressor is operated at the critical speed and helps prevent damage caused by vibration. After the critical speed is passed, the normal ramp rate is resumed. Some compressors have computer-based control systems. These systems often control ramp rates and make changes as needed to pass through critical speeds. Eventually, the compressor will be brought up to its minimum operating speed, which is the lowest speed the compressor can be operated at without causing surge or other operating problems. When the compressor reaches its minimum operating speed, the gas flow to the compressor can be started. Once the gas flow is started, the compressor can be brought up to operating speed at a rate prescribed by the compressor's operating. Once a compressor has been started and is operating properly, it should be checked routinely to make sure that it continues to work as it should. Operators should be able to detect common problems and see that action is taken to correct them. When you're checking a compressor, remember that it operates at a very high speed, so be extremely careful when you're working on one that's running. An important part of checking an operating compressor is listening for unusual sounds. Most compressors produce a high-pitched hum when they're running. An unusual raspy or squealing sound can indicate a problem with the bearing. It's also important to check the compressor's bearings for excessive vibration and overheating. These symptoms can indicate a possible bearing failure. The corrective action for surging is to increase the gas flow rate through the compressor. This can be done by recycling part of the compressor's discharge back through the compressor, or by routing the gas that's discharged from the compressor to another system for use or disposal. In addition to checking the compressor, it's also important to check the compressor's auxiliaries during operation. For instance, make sure that the oil level in the lubrication system reservoir is within the normal range, and that the oil is clear, not gritty or milky. In this example, the level's a little low, so some oil must be added. For this system, an air-powered pump is used to add oil to the reservoir. As the oil is added, the operator watches the level indication. He shuts the pump off when the level reaches the normal range. It's a good practice to note when oil is added and how much. If oil has to be added frequently, it probably means that an oil leak has developed somewhere in the compressor system. The oil pressure should also be checked. Low oil pressure can be an indication of several possible problems. Low oil pressure may indicate an oil pump malfunction or an oil leak. Higher than normal oil pressure can indicate a clogged filter or blocked oil lines downstream of the gauge. Check the oil temperature too. If it's too high, there may be problems with the lube oil cooler. Other indicators can also help identify compressor problems, so they should be checked frequently. In many facilities, indicator readings are recorded on a log sheet on a routine basis. These records are important because they can be used to spot abnormal trends, which can indicate that a problem is starting to develop. For example, a steady increase in the compressor's cooling system temperature may be an indication of a problem. Operating records can help operators determine when actions need to be taken to correct problems. If you find a potential problem while you're making routine operating checks, report it as soon as possible. Take any necessary steps according to plant procedures to prevent damage to the compressor system. Now, when a compressor is shut down under normal circumstances, the compressor is allowed to gradually slow down and cool off. It's just as important to monitor a compressor during shutdown as it is during startup. Checking for unusual sounds and vibration can help operators identify problems so that they can be quickly corrected. Keeping an eye on instrument readings is also important because they can tell you when problems are developing. After the gas flow has completely stopped and the compressor is no longer rotating, the compressor auxiliaries can be taken out of service. In this topic, we looked at compressor operation by focusing on startup, normal operation, and shutdown.